sperm that comes.
Three messages. So this
Hello, hello, hello. I think, can you hear me? If I could get a, thank you, thank you. Okay, great, great. Okay. Did I mention awkward? Okay, thank you for bearing with me. Yeah, I already kind of have this problem in my personality, but with this learning in the virus, which I still haven't gotten used to, I sort of feel like I can barely get the physics in because I feel like all I want to say every minute that you're here is thank you and I'm sorry, and thank you and I'm sorry, and thank you and I'm sorry. But all right, but in terms of physics, we actually did progress. This is the, for good or for bad, you're the section that tends to actually meet. I tend to not have conflicts with. So you're getting more burden, but maybe more knowledge or clarity too. Like I want to pick up from right where we were yesterday. Like yesterday, I think we made some progress. I think we started to see actually what we don't know, which is always the only way to know the next thing. And I think the breakout rooms can be torturous when they don't work, but they can be sort of productive when they do. So what we're going to do is we're going to hit you have all the notes from yesterday and all that. Yesterday, we sort of broke down a chart and everything for something that was thrown up at 50 meters per second. And we I know I didn't fill in every single number at the chart at the end. I'm going to, in effect, do that today. But to really test your skills or whatever, or your mettle, we're going to do, it's going to be almost the exact same thing. I'm just going to ask you to get to answers a little faster in a way. Anyway, here's the exercise for today is what I'm trying to say. What's on the board right here is the exercise for today. I am going to put you back in breakout rooms again. You are going to find that this is really similar to yesterday, like almost maybe upsettingly similar. Like yesterday, we threw up something at 50. Today, I'm throwing it up at 80. That's actually the only difference. Gravity is still gravity, physics is still physics and all that. So you could, again, make a chart out of this thing and copy all the numbers and copy everything from yesterday, and you'll probably be able to figure out the answer. Or I might encourage you to be a little bit more experimental or loose or creative, because this time I'm going straight to the point. I'm saying, here's the givens. Positive 80 is the initial velocity. Sorry, make this very clear. I'm saying assume V naught is positive 80, that G, which is A naught, is negative 10. But my question for this time is, by hook or by crook, I just wonder, how high does this thing get? Okay, how high does it get? That's what I want to know. I think it's very hard to do that in just one step. You're going to have to break that question down into sub questions that you have to figure out what you need to figure out in order to do that. But you have everything you need. Oh, sorry, I promise you have all the knowledge you need. It's all embedded in the 3 out of the 5 equations that we keep writing down. I understand you're up to lab 4 now, which is great and very helpful. And I know you've been warned that lab always progresses a little bit ahead of where we are. And the truth is that we always are ahead of where we are and behind where we are. In other words, you shouldn't have to look at any, you shouldn't have to look at any particular fact or anything from lab in order to figure this out. It's just things you've done in lab may reinforce it. But you can make a chart again, but it's just based on what we did yesterday. I just want to know, if you throw something up at 80, how high does it get? That's what I want to know, at least in the moment. And if it's clear that that's what I want to know, then I'm going to put you in breakout rooms and ask you to figure it out. Can I get a electronic? First of all, you can hear me, right? Someone did say that, right? Someone said they could hear me. Have I? Yes, they did. Okay. And is this clear? Even if you don't think you know you might. By the way, some of you, yes. Okay, I'll take it. Sounds good. And one other thing though, there may be some of you in the room right now. And look, again, there's always a diversity, a true diversity of where people are in any given class, right? Like everybody's in different places at every given moment, and it's even harder to tell where people are in this situation. But let me make this clear: if you happen to be a person who I'm just as worried about confusing people as I am boring people. Actually, I never know which one I'm more worried about, so that's a problem. But if you're a person who's sitting in the room right now and you're looking at this question, you're like, dude, are you kidding me? I totally have that answer in my head. And there may be some of you. I mean, I have the answer in my head. You might have the answer to this in your head. Now, some of you might think you have the answer in your head, and then it's going to turn out you're wrong. And I just hope that you're privately honest with yourself and you realize like you've got to adjust something. But some of you may have the answer in your head right now, and you may be right. And God bless America, if that's true. God bless you, whatever. That's great. But then your job in the room, and I do mean this for your own sake, so that you can get your tuition worth out of all this. If you have the answer in your head and you're pretty confident you're right, then when you go into the breakout room, your job is to convince the other people. Convince them of two things. One, that you are right. I mean, convince them that that's the answer and that they need seek no more. But two, convince them that you didn't just make that up or cheat, that they could get that answer too. Show them how you got it. Get them to get it too, and prove that by changing it again and saying, all right, look, even if Yaverbaum had said 200, I could show you how to do this. If Yaverbaum said it was 200, this is what you do. I mean, I do mean this, and I really mean it, because any of you who right now is already bored because you already see the answer, well, first of all, I definitely don't want to bore you. But second of all, I could tell you that you're the ones that will benefit the most from a conversation where you try to explain it to someone else. Like you will just be using them as a guinea pig anyway, for your own sake, I'm afraid. And those of you who don't see the answer right away, please do not despair, because that's what we're here for. And that is, and then if you don't see the answer right now, then that means no matter how boring or whatever this is, you will know the answer by the end of class, and then you will have gotten your tuition worth. And I feel like, what else do we want? So the question is, you throw something up at 80, how high does it get? Like that is the other joke is, by the way, I just published the notes from the other class and put it in your file. So like another way to approach this is you could totally flip through the PDF of the notes that I just put in the Google Stream, and you can cheat by looking through it, but it wouldn't be cheating because you'd just be looking at class notes. So whatever you want to do to get this answer and convince everybody in your room, you'll know you get the answer if you could do. I mean, that's the bottom line, is if you really can get it that fast, do it for 200 also, like for initial speed of 200 meters per second. And if you can get those, good, then come back and please let's all share it together. Okay, I'm putting in the breakout. I'm going to shut up. I'm putting in the breakout rooms. So please go once assignments. Good, awesome. Thank you. Thank you. Thank you. Thank you. Awesome. 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 Thank you. Awesome. Thank you. Thank you. Awesome. Awesome. Thank you. Thank you. Thank you. Awesome. Awesome. Hello. Oh, hello. Sorry. Can you? I am interrupt. Sorry to interrupt. Can you guys hear me? Oh,
Yeah.
oh yeah. Okay. Sorry. And I know my video just popped in a second ago. So, well, I'm just here to ask if you need more time or need help or need anything. Or are you the only? Or is everybody here? I mean, is like who? Is Rachel here? Had.
Yeah.
Oh yeah, you're here. Okay. So are you guys getting anywhere, or are you stuck, or are you done, or neither, or?
We spoke a little bit about it, but we're kind of, I think either done, but waiting for like to go out to the breakout room to see everyone else's.
Okay, fair enough.
Yeah.
That's all. All right,
Yeah.
fair enough. All right, I'll
Yeah,
go
I'm like
back.
kind of just going over everything like from the chart that we did just to make sure did it right.
Oh, cool. But you do. Oh, okay. But you do think, and I'm not going to ask you your answer, but you do think you have an answer then? Like you actually you got something.
Yeah.
Oh, okay. Okay. Cool. I mean, all right. I'll go back. I'll bring everybody back. Good to know. I didn't.
Okay.
All right. Cool. Thanks.
Okay.
Okay. Thanks. Bye. Okay. Okay. Hello. Hello. Okay. Okay. Hello. Hello. Okay. All right. So I know the breakout rooms have mixed effects sometimes and this and that. Let's get to does anybody, wait, let me say this also, by the way, because it keeps being, we're going to end early today is what I'm trying to say. But I've already posted, or by the time you're done with this class, the lecture from the other class from this morning will be posted on YouTube, and they're doing this exact same thing you're doing. And it shouldn't always have to be you guys that suffer, that have to be here the whole period when they miss sometimes. So we're actually gonna get through this and then end early today. I'm tempted to just say the answer almost, and then I'm thinking if I say the answer, that maybe then some of you will know you're right, and then maybe that'll give the confidence to explain, to share with the whole room what's going on. Unless anybody wants to share anything right now, like before I say an answer, can anybody either say a thought or a question, or how they started, or how they didn't know how, or where they got stuck, or like any comment about? I mean, I know partly it's easier if I do say an answer, but it's also easier if I don't. So anybody want to share any thought about this problem, like a possible answer?
I got 320 meters.
Yes, I got agreement with that. Yes. Well, you just made my day. Yes. Awesome. Okay. Wait. So now that's great. But maybe okay. See, I did. Awesome. Because again, with this Zoom thing, you all have to know. At any given moment, I really don't know whether it's super boring, easy, or super overwhelming, confusing, or and at any given moment, of course, half the people are out of their rooms for whatever their personal reasons. But that just means I don't have them. So I've no. So maybe it sounds like you guys don't think this is so hard. Okay, that's good. That is the right answer. So anybody who got that, or who was that? That was just was that Kimberly who said that? Can you explain?
Yeah, that was me.
Oh, great.
Okay.
Okay, yes, that's great. If you want to explain anything about that, that'd be awesome.
Okay, so my thought process was that, like, based on what we did yesterday, your instantaneous velocity at the peak height is going to be equal to 0.
Yes.
So I used the average velocity formula to find the average velocity at the peak height. So I did 80 plus 0 over 2
Yes.
to get 40 meters per second. You could use the acceleration formula to find the time too, but I just did it in my head because like you're doing 80 meters per second and going down to 0, and your acceleration is 10. So that would take you 8 seconds. And then I plugged the 40 meters per second into the average velocity formula, looking where you have the displacement. So it would be 40 meters per second equals x minus 0 over 8 to get 320 meters.
Nice. Seriously. Now, again, that's great. That makes it easier to teach this class. That's totally right. It is what we did yesterday, and I see that other people got the same answer too. So if it means that everybody's doing something similar, and I like that was there is also very what's the word, like dexterously explained. Like it was clear from the way she was explaining it. She was, even though she was saying she's using her notes from yesterday in the equations, I mean, which sure is good, and she was, but she was still talking like she had already assimilated it. Like she could have done it this way, but she did this in her head instead. Like that really did sound like some physics to me, honestly. And yes, that's the right answer. It makes me feel like, okay, we are getting somewhere here. Again, I know everybody is different, but if you got the answer 320, if you basically thought for anything like 8 times 40, then yeah, you're doing the right thing and you're doing what Kimberly just explained. Now I put it in the notes here too. Like this is just my written version of what you just said. Anybody is welcome to copy this or not, but this is what I'm showing everybody right now on the board. Is just my version of what Kimberly just said, but it literally is the same thing. It's not like even a different approach. It's just more words. And all of this is in the notes that I put in the Google Stream. So you don't have to, nobody has to race to copy this down right now or something like that. But it is showing, and it's funny, right here on this page that you're looking at, page 92, literally that's the moment when I did exactly what she said of like, well, I could do this in my head. I think I did actually, but then here is the equation explanation of doing it. In other words, I guess this is the one moment worth dwelling on. Yeah, like I'm asking everybody, how high is this peak height? It's a simple question, but it doesn't mean it's easy. Like, even if you're fast and do certain things in your head, like Kimberly did, still there's a number of things you have to do in your head to get this answer. And it is a multi-step process. The very first thing that in a way has to be, one very first thing that could be, the very first thing that could be, sorry, I'm losing my mind. This Zoom thing is so weird. Okay, I'm saying, hopefully what Kimberly just said made some sense, or hopefully some people already also thought it, like whether they were in the same room or other rooms. Hopefully what you're looking at the board, you're seeing a version, hopefully you're saying to yourself like, okay, I didn't write it exactly the way Yaverbaum did, like why does Yaverbaum always postpone the numbers to the last minute? I hate when he does that. Yes, well, I am recommending that everybody get in the habit of doing it, but right, that's the way mine looks. Maybe yours doesn't look this way. But it is, but what a lot of people will say is, okay, I get these physics problems. Once I see the solution, it makes sense. Or once I'm off and running, I know what to do next. I know what the equations mean. I know how to use them. But what people will say is, like when physics starts getting hard to them, which it does at some point to everybody, when it gets hard, people say, the thing is, I just don't know how to start solving a problem. I don't know which equations to use when to begin a problem or something. And of course, that is the art of the science. That is the hard part for everybody. And it isn't hard until it is. But not knowing how to start a problem is actually the only thing we're really, really trying to teach here. I mean, the thing we're really trying to teach here in the long run is how to start a problem, or in other words, how to know what to do when you don't know what to do. Like that really, in the long term, is the skill that we're trying to get everybody to get at whatever their level is. It's all about how to solve a problem that you don't know how to solve, right? And and that becomes particularly clear in problems like this, where what I'm asking you guys is something that you can't get right away. You have to invent mini questions in order to get to the final answer of that question. And the concrete point I'm trying to make is, if you look at the mini question here on the board right now, like when I solved this problem, I did something like what Kimberly said. I said to myself, all right, I need to know how far this thing gets by the time it reaches a peak height. I don't know that. I don't know how to do that. I don't know any equation that directly does that. But why don't I? Because of the very question, how far does it get when it reaches a peak height? It triggers in me the realization, like, not triggers, but it motivates the realization, oh, part of the issue is I need to know when it reaches a peak height. And even though I'm not even being asked that, I actually do need to know that, and I don't. So the sub question I'm going to solve first is, when does it reach a peak height? I solve for t first, even though no one asked me to do that. And I find what Kimberly said, that like I do have an equation that can get me there, and I can carefully do the equation out without really, I can just follow it. But when I step back and look at the answer that that equation gave me, it really does make sense. It's just saying in English, if you throw something up at 80 and you know that every second it's going to lose 10, well then by golly, it's going to take 8 seconds for it to lose everything. Like if you have 8 eggs in your pocket and you're losing an egg a day, then you have 0 eggs in 8 days. I mean, physical, actual eggs. I don't know why I'm saying eggs, and you can't fit eggs in your pockets anyway, but it's just that straightforward. And when you realize that's all the equation is saying, like what people will often do is be like, that's all it says, so that's a dumb equation. Like, what do I even need that for? Like, no, that's the point. All equations in the end are just trying to say something that you already knew, but they're trying to highlight how useful it is to follow that and use it later. So, okay, so we get that the thing travels for 8 seconds, like Kimberly said. It travels for 8 seconds, but then the next realization is, all right, distance equals rate times time. It travels for 8 seconds. I'm looking for the distance, but distance equals average rate of speed times time, and displacement equals average rate of velocity times time. So, and again, just summarizing what Kimberly said, we need the average velocity that it travels for those 8 seconds, and that average velocity is not 80. Right, that's just the beginning, very first maximum velocity. It never travels 80 again after that. It's continuously slowing down all the way to 0. So on average, it goes the average. So again, you don't have to copy this down but this is all to go to say, if you get a problem that when you get a problem, if you don't right away see how to get to the end, that just means it's a real problem. It doesn't mean that you missed a class or that the teacher missed part of the curriculum. Assuming things are fair, if you get to a problem and you don't know how to start, it means you got to just start somewhere and see what happens. And be willing to write down things that are wrong. Having said all that, yeah, I totally agree that the answer is 320. I'm going to say now, just for one more exercise, wait, sorry. So the answer is 320. I totally agree literally with everything Kimberly said in substance and tone. This is the way I did it. But again, these notes are in your Google Stream anyway. You could totally also make the one big chart and fill out the numbers and see this number pop up in that chart. Might do that in a second. But yeah, that's the answer. I want to do one more thing like this, but are there any questions on that at all? The answer is 320. If there's no questions, now I'm going to say, I feel like if we get, no questions. Cool. Thank you. Okay. Thank you. I appreciate it. Now I'm going to say, and again, no one has to jump up and scream about this, but if you're actually getting it, it's really true that once you get this kind of exercise or this pattern or this logic I'm saying, it does start to get to the point where you kind of can do this in your head. And it kind of is comforting and reassuring and good practice. So I'm going to ask one more time now. I'm going to ask just for you. I'm going to say, same deal, surface of Earth. We're standing there on Earth. Gravity is approximately 10 meters per second squared pointing down. So now I'm going to say to everybody, try to do this in your head. Like see if you can do this as fast as possible by what do you call this, math blast or like a mad minute or something. I'm going to say, let's just say you throw something up at 100 meters per second. You throw something up, at 200 meters per second. You throw something up at 200 meters per second. How high does it get? Like, as soon as you get an answer, either put it in the chat or raise your hand, or if you don't want to share it publicly, fine, but just say it loudly in your head. I want to see if the challenge here is, can everybody get this answer like with as little work as possible? Try to get it in your head, or just try to get it by jotting as little as you can on a piece of paper. But this is now a race, but it's not a public race. Just in your head, you throw something up at 200. How high does it get? I'll ask this. I want to see you electronically raise your hand once you think you have an answer in your mind. I'm not going to ask anybody what their answer is. I'm not. I just want you to honestly say when you think you have an answer in your mind. And once all the hands are up, I'm going to say what I think the answer is, and then like we'll move on or something. But I want everybody. So first of all, I want a show of hands that you can hear me right now. Like raise your hand electronically if you can hear me right now. Awesome, awesome. That's good. But I do want everybody. I'm being a jerk right now. I'm being a derivative of acceleration. Cool, cool. Thank you, thank you. That's a lot. That's great. Wait, oh, I'm not even, and I want gallery view. Hold on. Keep your hands up for a second. I want to see everything. Right, that's a lot. That's cool. So again, I'm just asking to raise your hand if you hear me at all. Cool. It looks like a lot of people are. And again, I'm also saying we are going to leave early today. So I'm just trying to get our bang for our buck here. Great. So everybody can hear me. So now put your hands down. Yes, put your hands down, please. Your electronic hands. Put them down. This is so weird. Oh my God. Okay, thank you. Okay, so what we're going to do now is I'm saying you throw something up at 200. I wonder how high it gets. The minute you honestly have any answer in your mind at all, and maybe you already do, then put your hand up. I'm not going to put you on the spot. I'm not going to ask you what that answer is. I'm not going to challenge your honesty. But just when you think you have an answer, put your hand up. And then once all the hands are up, I'm going to say the answer. But thank you. You get it. All right. Cool. So again, once you think you have an answer, put your hand up just so I know that you, and I won't call on you. I promise. I think this is like a new technique we're going to do. Yeah. Cool. Cool. Okay. Again, throw it up at 2. And by the way, if you're working on it, don't put your hand up. Take your time. I'm not, and that's the other, I'm not looking at names. Take as long as you need, but I just don't want to say the answer until everybody has. Okay. So, right. Cool. 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 So again, you throw something up at 200. We want to know how high it gets. And we want to see, cool. And we want to see either a thumb or a hand. Once you think you have an answer, you will not be asked to share it. Oh, we really need like a red light, yellow light, green light system, I guess. Like a, okay. Cool. Just keep your hands up. Once you have an answer, just keep your hands up. Once you have an answer, keep your hands up. Awesome. So you're throwing something up at 200. We want to know how high it gets. I'm going to tell everybody the right answer, but I'm not going to ask anybody. But once you have an answer, put your hand up. If you don't have an answer, you're trying to work on it, honestly. And don't worry, if I never see your hand up, I'm not going to embarrass you about that either or whatever. Because I know it's like some people might be out of the room. I get it. But just, if you're, and this is why I really need I need a 3 signal system for this really. But so you throw something at 200. How high does it get? All right, I'm going to say, so I'm going to say the answer in one moment, I think. Oh, cool, cool. And all the participants raise their hand. All right, cool, cool. All right. So I think the answer, I'll put in the chat. I think the answer, and I better be sure about this right now. I'm like on the, so I think that's the answer. Yeah. Oh, yeah. Oh, I like the yay. Oh, that yay gives me a yay. Oh, that's great. Right. And you can put your hands down. You can react. Now, I think that's the answer. I'm not going to ask you if you got it right or wrong, but does anybody, and if you got it right, you should congratulate yourself, especially if you got it in your head or whatever. And I'm not saying this is all of physics, but it's good if you get that, if you can picture that. And then you should be proud. Does anybody want to ask me a question about, so I'm saying, I don't remember what I said. The answer is 2,000 meters. Where did I get, what I did in my head was I said, if it's thrown up at 200, and then it goes from 200 all the way to 0. On average, it goes 100 meters per second. If it's thrown up at 200, then on average, on its way up, it's going 100. But also, it's true that if it's thrown up at 200, that means it's going to take 20 seconds to get to the top because it's losing 10 every second. It's 200 divided by 10 is 20 seconds to get to the top. So we've got something going on average. I don't remember anymore, 100 meters per second, and doing so for 100 seconds. So it's 100 seconds times 20. I just said it backwards, but Yeah, 100 meters per second times 20 seconds is 2,000 meters. That's how I got it. Let me also ask, how fast, no, sorry. How far does it go in the very first second? How far does it go? And you don't have to raise your hands or anything. Just think about this for a second. How far does it go in the very first second, like from t equals 0 to t equals 1? In the very first second, it would go, I think, 195 meters, right? The average of 200 and 190, because it's like I'm picturing a chart in my head, in effect. But I'm not like literally a chart, but does that make sense, right? I'm saying that this is how constant acceleration works. We're gonna, and it's good. I think you guys get it. If I can put together, so if you see how it doesn't matter what the numbers are, the method is still the same. We're doing like 3 steps. This method of resolving accelerations and velocities in order to get displacements. We're doing the same method in our head every time, and we're getting faster and faster at it, it looks like, which is great, but it is like a 3-step method. We're getting like using acceleration to get time, and using time to get average velocity, and then so we could actually make this even faster. And this is the last thing we're going to do today. I want to say, if you notice what we're doing every time, like all this is coming down to is you've all your life known distance equals rate times time. Now we're expanding and making more sophisticated that notion. We're saying, yeah, distance equals rate times time. But first of all, what that really means, but there's like different kinds of rates. The rate itself might not be steady. The rate might change. We call that acceleration. And then that acceleration rate might change. We call that a rate of jerk. And each one of those rates we call a derivative in calculus class, and they can go on forever. So distance equals average rate of speed times time. What we're here to solve for in physics is situations where what you really know are not the average speed. What you know as a constant is the acceleration. What we're showing ourselves is that as long as we know the acceleration and the initial velocity, then in some amount of time, we'll know how far something can get. That's what we've been doing, okay? But we've been doing it by using 3 equations in succession each time. I want to now quickly put those 3 equations together into one so that we don't have to do this every time. In other words, every time we've been in effect. And this is why some people get it faster than others, because it is like a number of steps that you have to simulate. But we've been doing every time, we've been saying, well, displacement equals average, well, sorry. Sorry. Well, yeah. In effect, and again, I'm actually saying that we're going to leave early today. We actually are in a couple of minutes. But let me show you what's been happening in these exercises, which could be done through a chart or through a graph. But each time we're saying displacement equals average velocity times time. Average velocity we're getting by averaging an initial and a final instantaneous velocity. And each time we're getting the final instantaneous velocity by using acceleration. So in effect, we're using these three equations, but we're rearranging them either in our heads or on paper and then putting them together and then plugging in numbers one at a time. If we really followed like the sort of model that we're ultimately trying to put forth here, if we really follow the method of problem solving in physics where you postpone the numbers till the end, then we could actually put these equations together before we even see the numbers. In other words, I'm going to say like displacement equals average velocity times time, right? Like that's just a rearrangement. That's just from the other page. And but of course, this all assumes this. The reason we're focusing so much, the reason we're focusing on gravity problems is this equation that idea that you can average the velocities in order to get average velocity. That is only true when acceleration is a constant. And acceleration is not always a constant, but it is in free fall. So that's why we focus so much on free fall. That's why you have lab 3 and lab 4 are both so focused with free fall, because it's a reliably constant acceleration situation. But so in such situations, we say this, but then we say, from the previous page, like final velocity can be gotten from acceleration, right? So we substitute in, well, here, again, this is just from the previous page, but right? So I'm just substituting in, and we're almost done for today, but I'm taking that, and this, by the way, technically what I'm doing now is new. Like this is not review. You may have seen this in high school or in the textbook or something, but whatever I'm doing right at this moment, I did not do last week. And this explicitly, I don't think anybody's done in lab. So I'm not referring to something I think you already know. I'm showing you something or doing something, but I'm saying, I'm taking the three equations that we do know and arranging them together algebraically. I'm putting AT plus B naught, substituting it in for V up there, like the arrow says. And then now I'm collecting like terms here. I have V naught plus, I have V naught plus AT plus V naught again. Well, I'm going to go to that so I can rewrite. Okay. And then I'm going to distribute the T again. And I know for some of you, this is like pulling teeth that I would explain this kind of algebra. And for others of you, it's pulling teeth in a different way. Like talking about algebra is torturous in a way to everybody, because if you already know it, then you're bored. And if you don't know it, then it's like annoying and confusing. But it's the way it is. This is the, and I don't know why I'm being so, I'm still struggling with the Zoom thing, I guess, to be honest, because I would love talking. If we were in a classroom right now and I were doing this on the board, this would actually really excite me, to be totally honest, but I can't see how it could be exciting anybody right now. But anyway, we have this last line, x equals parentheses AT plus 2V naught all over 2 times T. So I'm going to distribute the T is what I was saying. And I get I did it back then. Okay, this is an equation. If we're keeping track or whatever, this would be equation number 6, if you like. Okay. In a way, it's a super common, super familiar equation of physics. Again, if you took physics in high school or something, you may recognize it. People do use it all the time. Sometimes people overuse it. Sometimes people use it when they shouldn't, blah, blah, blah. But it is a very common physics equation. It's just usually called this thing, x equals 1/2 at squared plus v naught t, is often called the equation of motion. It's, I mean, all equations in physics are equations of motion, but this is the equation of motion for any object that is moving with a constant acceleration. This is like the distance equals rate times time version. I mean, this is the version of distance equals rate times time for any situation where the rate that is known and reliable and steady and constant is an acceleration rate, okay? And this you can just plug in into one fell swoop whenever you want, whenever you know acceleration and velocity and you want to get displacement. Like in the last problem, we knew acceleration was -10. We knew the initial velocity was 80. We want to know its displacement in a certain amount of time. We could just, in 8 seconds, we could just literally plug in 8 squared is 64. 64 times 5 is 320. Something very strange about what I just said, but I'm going to keep moving anyway. This is the equation of motion. You don't ever need it. Here's the other thing. We just it's not new information. It is a shortcut or a technique. You can always from here on in plug into it whenever you can, whenever you think you have the information that it requires, and you can always rearrange it. It does in 1 step what we've been doing in 3 steps up until now, but you never actually need it if you don't want it, because it is just that, just a shortcut. It's just the information of the other equations smashed together into one. And by that reasoning, or in that same spirit, I want to give you one more equation that's a shortcut, and you'll see why. But they're both double equal sign. They don't contain new information. They just contain the old information packaged in a useful way. And then we're going to stop. Now, why do you need one more equation? Well, in a way, you don't. Everything of these kind of problems, every kind of constant acceleration problem could be solved with just the equations we have so far. But the one situation can arise, in fact, a situation can arise where you're being asked something like displacement, but instead of being given time, you're given other information. In other words, there can be a situation, every single one of these equations we have so far makes reference to time. I guess that's what I'm trying to say. Every single equation makes reference to time. What if you have a physics situation where where you don't know the time and you're not solving for it, like where t is just a simple unknown and it's irrelevant? Then it would be nice to have an equation that didn't make any reference to t at all. Oops, sorry. Like every equation has a t in it. So if you don't know the t, you can rearrange an equation and solve for t. But if you don't know t and you're not being asked to solve for t, if you neither need nor seek t, then all those equations will bring you to a dead end. It would seem, unless you could somehow solve them simultaneously, like so. Oh, and in fact, that really was the situation we have at hand. If you think about it, even today, we said something's thrown up at 80 meters per second, and it's losing velocity at a rate of -10. And I asked, how high does it get? The reason that's actually a hard question, or maybe it actually wasn't hard for this group, and I totally realize that, and that's great. But the reason it's an involved question that we look back at our notes and look at the chart is because it is a three-stepper. Like, I'm not asking about the time, but it seems like you need the time in order to get the answer. And you do, like in every method we've done so far, in order to get the answer I was asking for today. Oh, sorry, I didn't even write. I said, really, what almost could even maybe feel unfair if you didn't have all these charts and everything is I say, here's the initial velocity, here's the acceleration. What's the height? What's the distance? I'm not giving you any information about the time, but I'm also not asking about the time. So it was incumbent upon you guys or Kimberly and everybody else to like go through this walk to figure out the time and then use that time to get the answer. And then there's no gratification in the time. It was never the reward. Like I didn't then at the end give you extra points for having the time. So wouldn't it have been nice if we could just end run that entirely? Like, since the time didn't seem to be the thing, wasn't it unfortunate that we had to run through 3 equations and put them together, each of which was locked together by time? What if we could just do that all in advance? In other words, and this is the thing we're going to do right now, and this is going to generate, in other words, I'm going to generate an equation that doesn't have any t's in it at all, and we can use that from now on as a shortcut to solve problems like this. And that's where we're going to end today. And the way I do it is, again, just take those 3 equations and put them together in a different way. I'm going to say, oh yeah, well, same 3 equations as before, but now I'm going to rearrange. I'm going to rearrange this one and say, okay, fine. Like, again, that many of you can do in your head, but many of you can't. I cross multiplied and then divided so that now a is in the denominator and t is what I'm solving for. Like, I just rearranged that equation. And in English, that's like saying that's the English version of saying it would take 8 seconds for the 80 meters per second throw to reach a height, a speed of 0. But anyway, so we have that, right? And now, and do the same thing as we did on the other page. Do this, right? So now I'm gonna put this together with that. I'm going to substitute one into the other on the next page. Okay, and tell me if you want me to go back. I'm looking at the chat. Tell me if you want me to go back. But again, this is the last thing we're going to do today. It's not ending as early as I might have led you to believe. I apologize, but we will not end late. So I'm saying. And now what I have on the top, if you think about this, is like the top, well, if I foil it out, sorry. Okay, like I'm just foiling out the top, but then I find I have a v squared minus vv naught plus vv naught, or however you write it. And so those two terms cancel out. So on the final page, on the last step of this, I get so this literally does say x equals, like, so the displacement that something covers between any 2 points in space and time, how far something gets from like this moment to that moment, x, is its final instantaneous velocity speed squared minus its initial instantaneous velocity speed squared all over twice the acceleration. This equation, more than any of them, this equation in and of itself really seems like a formula. Like this seems like a formula, because even I mean, I taught it for years, but if I look at it, it doesn't tell me anything to physically picture. I don't look at it and say, oh yeah, that makes sense. Like I do, but I don't, and I certainly don't expect you to. I don't look at this thing and say, of course, obviously that would be true. No, and it's not a triple equal sign. Like it's not the definition of anything. It's not a concept. This is just an algebraic result that says, because we believe all the other concepts, because they actually do make sense, the algebra then means that if I ever happen to be solving for an x, and I don't know the t, and I don't care, but I just have a and v naught, then I can plug into this and get out the x. It can be used for plug and chug. And it's always right. I mean, it's a double equal sign, but it's always right as long as we are talking constant acceleration, as long as there actually is an a to plug in between those 2 points of time, an a that remains steady, then this will work. So like the check is like today, the final velocity that we were looking for was 0. The initial velocity was 80. So it's 80 squared is 6400 over negative 20, and 6400 over negative 20, sorry, negative 6400, because there's a negative sign on top, over negative 2 times 10, so it's negative 20. So negative 6400 over negative 20 is positive 320, the answer for today. I'm saying that quick because I want to get off the line for the sake of all you guys. But that's our last equation. There's no more constant acceleration equations. I say we have 7. 2 of them assert the connection between all this and calculus. The connection is we are, if you get calculus at all, the thing is we are studying phenomena in space, and we as physicists believe in derivatives. We believe that for any function, you can take a derivative and you get a new function, and you can take a derivative of that and you'll get a new function, and you could take a derivative of that forever, 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 thanks to calculus. In physics, we're saying we're focused, when we look at problems occurring in space and time, we tend to be focused on derivative number 2. We're looking at situations where there is a first derivative of position with respect to time, like where there is a velocity, and that velocity is changing. So there is a second derivative of position with respect to time, where there is a derivative of velocity, but where that derivative is not changing. We in physics are focused on the second derivative because that's what we feel in nature. And this is the last equation for solving problems of that kind. 2 of those equations assert the calculus. The other 5 are super useful in problem solving, including this one. Okay, I've kept you late for being early. Like it's 1:20, but I'm going to hop off if that's okay. Yeah, I'm going to send you these notes and I'm going to post the video tonight. Or could I just, yeah, are we cool? I mean, is there any, of course, if there is a question, actually, I'd like to answer. Is there any question or anything, or is this cool? Or could I get either a thumbs up, a hand, or a okay, sounds good to me. Thank you, Kimberly. Sounds good. Great. Thank you, Erica. Okay, we are done. You are good people. Thank you. No, thank you. Seriously, ye shall inherit the earth. And I mean it, and I don't mean meek in the dumb 21st century way. I mean meek in the deepest, most profound way. You are the earth inherited. I mean, you are the wise ones. Okay.